Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. We are starting a deep dive into the magnetic properties of materials from Unit 5, magnetism and matter. Now, for many students, this unit can feel a bit confusing, all those vectors like B, H, and M, but our promise is that we will make this entire concept logical, easy to remember, and completely exam-safe for you. So let's start with a simple question. We all know a magnet attracts iron very strongly, right?
Yes, of course.
But tell me, why is it that some materials, like wood or plastic, seem to have no magnetic property at all, while others, like copper or even water, are actually weakly pushed away, repelled by a strong magnet?
Wait, really? Water's repelled by a magnet. I always just assumed that if something wasn't attracted like iron, it was just non-magnetic. Why would water or copper actually move away from a magnet? That sounds very strange.
Exactly. And that's the door into this chapter. We always focus on attraction, but this repulsion is just as important. Think about it like this. If you take a copper coin and drop it between two very powerful magnets, it doesn't just fall freely, it descends slowly, almost like it's swimming through something thick.
So something is pushing back on it.
Precisely. The field is pushing against it. This happens because magnetism isn't just for a few special materials. It's a fundamental response that every single material shows. Attraction, repulsion, every atom reacts.
Right.
Okay, so let's unpack the core idea behind all of this. At the most fundamental level, the principle is actually quite simple. Magnetism is created by moving electric charges. That's it.
Moving charges, so like a current in a wire.
Exactly like that. And this means that everything we see, strong attraction in iron, weak repulsion in water, it all comes down to how electrons are behaving inside the atoms. You see, electrons are constantly moving, they are spinning on their own axis, and they are orbiting the nucleus.
And those movements are like tiny, tiny currents.
Perfect. They are atomic-level currents. And the differences we observe in materials just depend on how these tiny electron motions add up. To help you visualize this, just think of an electron as a tiny spinning top.
Okay.
That spin creates its own mini magnetic field. You can imagine a tiny invisible halo of force around it. We call it an atomic dipole. Now, in most materials, like wood or plastic, these halos are all pointing in random directions. They completely cancel each other out.
So the material appears to have no magnetism.
Right. But in iron, something different happens. Trillions of these little halos, these spinning tops, they line up, they act like a synchronized formation, and all their tiny effects add up to create the powerful magnetic field we can actually feel.
So, for thousands of years, people thought magnets were just magic rocks, but the real breakthrough was realizing that this magic was just connected to electricity, that moving charges create magnetism.
Precisely. That profound insight Ørsted's discovery was the key. We just needed quantum mechanics much later to explain that an electron's spin and orbit are the atomic currents that keep permanent magnets working. It's not magic, just organized motion. Now, since every material responds to a field, we need a way to measure and define that response technically. This is where Ørsted introduces three very important vectors: B, H, and M. So let's start with the material's response. Could you please read out the formal Ørsted definition of magnetization, M? Yes. We define magnetization M of a sample to be equal to its net magnetic moment per unit volume. And the formula is M equals M net divided by V. Very good. So M is basically how much the material itself is magnetized. It's the density of all those tiny aligned atomic dipoles we just talked about. Now, the total magnetic field inside a material, which we call B, is actually made of two parts. Two parts? Yes. The first part is the field from external sources. For example, the current you run through a solenoid wire. We call this the magnetic intensity, H. Think of H as the external driving force. It's the field that is trying to align the material. The second part is the field the material contributes itself. And that's M, the magnetization. So you apply H, the material responds with M, and the total magnetic field B inside is the sum of both. The main equation is B equals mu0 times H plus M in parentheses.
Oh, I see. So H is what you apply from the outside, M is the internal reaction, and B is the total result.
That's the perfect way to remember it. Always remember this for the exam. H drives, M responds, B is the total. H comes from your external current. M is the material's internal alignment. B is the final total field you measure. And to see just how important M can be, think about this example. Let's say we have a solenoid. We pass a current and it creates a field, H. Now we insert an iron core. Iron might have a relative permeability, μ, of say 400.
That's a huge number. What does it mean?
It means the material's magnetization, M, is so incredibly powerful that the total field B inside that iron core is now 400 times stronger than the field H from the current alone.
Wow, so the iron is actually amplifying the field by that much.
It's massively amplifying it. The M is huge compared to H. Hope everything is clear so far. This concept explainer is from profsam.com. That is PROSSAM.com. All right, so now that we have this BHM frameworks, we can classify materials. The strength of the response, M, to the driving field, H, is measured by a quantity called magnetic susceptibility, Chi.
Susceptibility, so how susceptible it is to being magnetized.
Exactly. It tells us how easily a material can be magnetized. And based on the value of Chi, we get our three main types: diamagnetic, paramagnetic, and ferromagnetic. Let's start with diamagnetism. These are materials like copper, water, and gold. Their susceptibility, Chi, is small and negative. This means they are weakly repelled by a magnet.
Okay, so the repulsion we talked about at the start.
Yes. And it happens because in these atoms, all the electrons are in pairs. So there's no net magnetic moment to start with. When you apply an external field, it induces a tiny magnetic moment that, according to Lenz's law, opposes the applied field. That opposition is what causes the weak repulsion.
So it's like a defensive reaction trying to cancel the field.
Precisely. It's a fundamental induced repulsion. In fact, superconductors are perfect diamagnets. Their chi is -1. They expel the magnetic field completely. That's the Meissner effect. Next up, we have paramagnetism, materials like aluminum, platinum, and oxygen. For these, chi is small but positive. This means they are weakly attracted by a magnet.
So what's different in their atomic structure?
Unpaired electrons. Because they have unpaired electrons, their atoms already have small permanent magnetic dipoles. When you apply an external field H, these permanent dipoles try to align with it. But this alignment is constantly being disrupted by thermal motion. The heat energy just jumbles them up.
Ah, so that's why the attraction is weak.
Yes. And it's wild. If you heat up a paramagnetic material, its magnetic property gets even weaker. Curie's law describes this. And finally, we get to ferromagnetism, the real powerhouses: iron, cobalt, and nickel. Their chi is huge and positive. They are strongly attracted, and most importantly, they can remember the magnetism. They can become permanent magnets.
And this is because of those domains you mentioned.
Exactly. The key concept is domains. They have so many unpaired electrons that a quantum effect called exchange interaction makes neighboring atoms spontaneously lock their spins together. They form these huge, synchronized regions called domains. When you apply a field, these domains just rotate and align. And because of that strong locking force, they stay aligned even after the field is gone. This entire framework shows how the simple moving charges from Unit 4 create these complex material properties here in Unit 5. It sets the stage for everything that comes next, like electromagnetic induction. Okay, now let's talk about the silent killers. These are the concepts that seem obvious but can make you lose marks in the exam.
The common mistakes.
Right. Misconception number 1. Students often think magnetic poles are charges. Like a north pole is a positive magnetic charge.
I can see why people think that. But
Yes.
if you break a bar magnet in half, you just get two smaller magnets, right? You don't get a separate north and south pole.
Exactly. And that is the correction. Magnetic poles are not charges. They are just regions where field lines emerge or enter. The moment you cut a magnet, new poles form, because magnetic monopoles simply do not exist in nature. The field lines must form closed loops. Misconception 2, which we touched on earlier. Students think only iron, nickel, and cobalt are magnetic, and everything else is non-magnetic.
So the correct idea is that all atoms are magnetic because all atoms have moving electrons. It's just that the effect is usually very, very tiny.
Absolutely right. The difference is not the presence of magnetism, but the alignment and permanence of the atomic spins. And the final killer. Students assume that if you put a paramagnetic material, like aluminum, in a strong field, it will stay magnetized afterward.
I see. But it won't because of the thermal motion, right? The heat just randomizes the alignment as soon as the external field is gone. But for ferromagnets, the domains keep them locked in place.
Precisely. You've got it. The key thing to remember is paramagnets forget when the field leaves. Ferromagnets remember. Magnetization in paramagnets is temporary. It's quickly destroyed by thermal randomization. Okay, to lock all of this in for the exam, let's use some simple memory anchors. First, for that fundamental relationship, just chant this to yourself. B equals mu0, H plus M in parentheses. It'll help you remember the vector addition of the fields.
Okay, B equals mu0, H plus M in parentheses.
Good. Second, for the field line pattern of a bar magnet, use this phrase. Inside, south to north. Outside, north to south. Complete loop, opposite directions.
That's helpful. It covers both inside and outside.
And finally, a physical gesture. For diamagnetism, push your hands away from each other. That's repulsion. For paramagnetism, slowly bring your hands together. That's weak attraction. And for ferromagnetism, lock your hands in a firm handshake. That's strong, persistent attraction. So to summarize our deep dive, here are 3 exam-safe factual billets. Point 1. Magnetic behavior is classified based on response. Diamagnetic are repelled with chi less than 0. Paramagnetic are weakly attracted with chi greater than 0. And ferromagnetic are strongly attracted with chi much, much greater than 1. Point 2. Magnetism originates from moving charges, specifically the spin and orbital motion of electrons. Unpaired electrons are the key to permanent atomic dipoles, which you find in paramagnetic and ferromagnetic materials. Point 3. The total magnetic field in a material B is a vector sum of the external driving field, H, and the material's internal response, M. The formula is B equals mu0 times H plus M. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Study hard, understand the concepts, and all the best for your exams.